Yeah? Right?
Average and mean are the same thing. Average and mean
It is the same thing. The average is another word for the mean. Right? Okay. So I get this 2 into 1 upon 5 plus 3 into 1 upon 5. I can write this like this because I've got this, can write 2 upon 1 plus 3 upon minus 1 upon 5, right? I can write it like this. This can be written as 2 upon 5 into 1 plus 3 upon 5 into minus 1. Sure? Now think of what is 2 upon 5 and what is 3 upon 5. What is 2 upon 5? What is 2? Number of wins. 5 is the total number of times I played the game. So 2 by 5 is known as the relative frequency of wins. 3 by 5 is the relative frequency of losses. What is 1? The value of my random variable. Minus 1, the value of, so my random variable takes values plus 1, minus 1. 2 upon 5 is the relative frequency of 1s. 3 upon 5 is the relative frequency of minus 1s. If I multiply each value of the random variable by its relative frequency and sum up, I get the arithmetic mean or the average. Right? So what's an average? In the context of a random variable, you take each value of that random variable, multiply it by its relative frequency and sum. Sure? That is very clear? Right? For example, the average of 3, 3, 4, 6, 9 will be what? I have got 3 twice, out of 5. So 2 upon 5 into 3 plus 1 upon 5 into 4 plus 1 upon 5 into 1 upon 5 into 6 plus 1 upon 5 into 9. Because it would really be this, no? 3 plus 3 plus 4 plus 6 plus 9 upon 5, right? So it would be 2 into 3 plus 4 plus 6 plus 9 upon 5, which will be nothing but 2 upon 5 into 3 plus 1 upon 5 into 4 plus 1 upon 5 into 6 plus 1 upon 5 into 9, right? Sure? So basically my arithmetic mean is nothing but each value of the random variable multiplied by its relative frequency and sum. Now think of a situation where you are playing this game not 5 times but say 5 million times. Yeah? When you played this 5 times, what was the relative frequency of ones? 2 by 5. So about 40% of the times you got 1. 60% of the times you got minus 1. But if you play this 5 million times, for example, do you think the proportion will still remain the same? 40% times loss or gains, 60% times wins. Will it remain the same if you played this 5 million times? No. So what would they be?
Will be closer to the actual mean.
It will be a normal distribution.
No.
Equal number of wins and equal.
So you, in the very long run, you would expect the proportion of losses and the proportion of gains to be equal.
Yes.
Yeah, because you're playing this many times and the coin is a balanced coin. Is that clear? So what would the relative frequencies then be? 0.5, 0.5. Right? So the idea is, as the sample size becomes larger and larger and larger, the relative frequencies will get closer and closer to the probabilities. You see the point? As the sample size becomes larger and larger and larger, the relative frequencies with which each of the random variables occur will get closer and closer to the probabilities which you found from that underlying theory. Right? That's a very important result. Because in general, in this simple case, you know the set of all possible outcomes, the sample space and the function, all that's happening. In the real world, when you're simply collecting samples and calculating arithmetic means, you have no idea what the real the real world distribution is. You see the point? And so really, you have no way of writing the entire set of, possible outcomes and defining that function and then working back to the probabilities of random variables. But this says as the sample size becomes larger and larger and larger, the relative frequency will actually start approximating those probabilities better and better and better. Yeah, this is a very important result. So what it means is, as the sample size becomes larger and larger and larger, the arithmetic mean will get closer and closer to the expected value as n becomes larger and larger and larger. So if a sample of size n, if you form the arithmetic mean, right, and as n becomes larger and larger and larger, the arithmetic mean will get closer and closer and closer to the expected value. Right? So the expected value in a sense is where the arithmetic mean will go if you had an infinitely large population. Is this clear? Sure? Okay. Now why is this important? Suppose I want to find the per capita income in Mumbai. Okay? That is how much does an average Mumbaiker earn. I can find that number theoretically. That is, to find that number theoretically, what we'll have to do? I'll have to go to each person, ask them how much they earn, right? Okay, if you want to really make sure they give you correct answer, you have to ask them to share all their bank details and everything with you, so you can go home and really check whether those people earn that much, right? So, how do you reason? Suppose you can go to each Mumbaiker and get that data. Then you add all those and divide by the total number of people in Mumbai, you will be able to know what the average Mumbaiker actually earns, right? Sorry, yes? Now, can you actually do this? You can't do this, right? Because it's well nigh impossible. So what will you do? But that's an important question. You might want to know how much does an average Mumbaiker earn? What's the average standard of living in Mumbai? It's an important question. So if I wanted to know that, what would I then do?
Just take a sample.
I'll take a sample. So maybe I'll take, say, some 100 or okay, and I will calculate the arithmetic mean. Right? Now, two important considerations are there. The actual number that I am trying to find out, the actual per capita income of a Mumbaiker, the average income of a Mumbaiker, is not a random variable. It's not an outcome of a chance experiment. It's a fixed number, isn't it? If I have to do this exercise again, then that number won't change, right? But when I'm thinking of taking a sample, right? The sample is an outcome of a chance experiment. Who comes in my sample is purely by chance, right? And therefore the sample mean that I will get is an outcome of a chance experiment, so it is a random variable. It will have a probability distribution and all that, right? So it's fundamentally a different quantity, right? That something that I want to know there is a fixed number, right? Right? Which doesn't vary from sample to sample. Whereas what I can know, I can never know that number. I can only know the sample mean. But the sample mean is a fundamentally different quantity. It's a random variation. It will vary from sample to sample. It will have a probability distribution. Right? So, the question then is, what is the connection of my sample mean to that quantity that I am looking for out there? What is the connection of my sample mean to that quantity that I am going to look for out there, right? That quantity that I want to know is something I can never know fundamentally, right? I can only make a guess at it based on a sample. The sample is a guess, so it will vary from sample to sample because the guess is made on the basis of certain information. What is that information? The sample that I have, right? Okay. Now the sample that I have will change every time I take a different sample. Suppose the sample is based on a size 1000. Next time I pick up some other 1000 people in the city. Next sample will involve another 1000 people in the city. So I get different samples each time. I'll get different samples each time, right? So the point then is, suppose I get a number 6342. I say मैंने sample लिया 1000 लोगों का और उसका average है 6432. Will you accept this claim at face value? Will you say that the average income of Mumbai is 6342? No. Why? Because you say some other 1,000 people have taken and that income turned out to be 7,962. Whereas he went and took some other sample and it turned out to be some 4,859. Whereas he took some sample and it turned out to be 8,000 something. So problem is the sample will vary. The sample mean will vary from sample to sample. Whereas the quantity I want to know will remain fixed. So the next question I must answer is, what is the connection between this sample mean and the quantity that I want to know out there? And that's where what we saw here becomes important. As the sample size increases, the sample mean will get closer and closer to the expected value. So the expected value is nothing but what the sample mean would become if your population size was infinitely large. Right? But if you take an infinitely large sample from the Mumbai population, what would you get? You know what the real per capita income in Mumbai is. You can in principle take an infinitely large sample from a Mumbai population of say 1.5 crores. How can you take an infinitely large sample from Mumbai population of 1.5 crores? If you have a finite population, can you take an infinite sample from that? Yes. If the sampling is with replacement. So I pick up Aniket, I count his income, put him back in the population. I pick up someone else, calculate their income, put them back in the population. If there are 10 people, I can pick 20 people like that from those 10 people at random. All that I want is a random selection. That is, at each point of time, everybody must have the same chance of occurring. Right? Like there is 1 kilo of rice. 1 kilo of rice. You pick up a sample of 100 grams. Right? You pick up 1 grain at a time. You pick up 1 grain at a time, weigh it, put it back. Like that you can collect infinitely many grains from a pot full of grains. Right? So you can take an infinitely large sample. So the point is, if I were to take an infinitely large sample of Mumbai population and calculate what I get from the sample, what would that be? That would be the actual income in Mumbai. So what this has said is, this has said that as the sample size becomes larger, the sample mean gets closer and closer to the population. Okay, it's a very important idea and we have to use it a lot. Why? Because, see, this property is called consistency. Why is it called consistency? Because the idea is there is an unknown quantity out there. You have to make a guess at that unknown quantity. You cannot make that guess. You make the, you can't know that quantity for sure. So you have to only make a guess. You will make a guess on the basis of some information. And what this is telling you now is that your guess has an important property. That as the information that you have keeps on increasing, your guess will get closer and closer and closer to the true value. Yeah, as the information increases, your guess will get closer and closer and closer to the true population value, the true quantity that you want to know. Right? Okay? Is this clear? This is called the property of consistency. And it tells me that the arithmetic mean has that property. It tells me that the arithmetic mean has that property. That is, as the sample size increases, the arithmetic mean will get closer and closer to the true population mean which I want to know. Okay. This gives a clue. Suppose there is some unknown quantity I want to figure out. Right? There is a way in which I got some information. Right? I want to make a guess at that unknown quantity. Then this tells me that if I consider some sort of an average which corresponds to that quantity based on my sample, right? And as my sample size increases, I must have that property that my guess will get closer and closer to the true value that I want to find out. Right? Okay? Arithmetic means sabko malum hai na, average. Okay. Now, so just keep this at the back of your mind. This is going to be a very, very important idea. It's actually called the law of large numbers. Right? It's actually an important theorem which is called the law of large numbers. At some point we will also be able to in a position to actually formally prove it. But the law of large numbers is a very, very important idea. It says as the sample size becomes larger and larger and larger, the sample mean will get closer and closer to the population mean. Okay? The law of large numbers. Okay. Now, let me introduce to you another idea. Let's first understand some basic interesting things about the arithmetic mean in any case. The arithmetic mean has other important implications. Okay. Think of a collection. Suppose think of a collection of numbers. Say 1, 2, 3, 4, 5. Okay. But before maybe we come to this, let's think a little bit carefully of the idea of a distance when you think of numbers. So let me go back to my old tried and tested example, right, of a highway, right? There is this milestone number 0 here. There is this milestone number 1 here. There is this milestone number 2 here. You live here, your friend lives here. Right? So this distance is 1 mile or 1 kilometer if you want. 1 kilometer, right? Okay? Sure? On the milestones. Now if I ask you, what is the distance of your friend's house from your house? 1 kilometer? Yeah? Why is that the answer?
Because we have basis from
2 minus 1. So the milestone in front of your friend's house is 2 and the milestone in front of your house is 1. So if you want to find the distance from your friend's house to your house, you must take the milestone on your friend's house, subtract from it the milestone on your house, you will get 1. Okay. Now so what's the distance from your house to your friend's house? By the same, it's an algorithm that you use, right? When you want the distance from F to Y, you take the milestone in front of F, subtract from the milestone in front of Y, and you get 1. So, by the same algorithm, what will be the distance from Y to F? 1 minus 2? You get minus 1? It's a problem, no? Because we are saying two interesting things. One, we are saying that the distances can be negative. And the secondly, what we are saying is distance from Y to F and F to Y on a straight line will be
absolute number.
Yeah, so therefore we need to think of distances more carefully. One way of thinking of this is to simply take the absolute number, right? Another way, which works only partially in this case, is Y minus F square, right? Y minus F square is not a good idea because if you're a third person staying here at 3, then this formula says t minus y, the distance from t minus y is 3 minus 1 square is 4, right? Whereas distance from t to f is 3 minus 2 square is 1. Distance from f to y is 2 minus 1 square is 1. So it says its total distance is 2, right? Whereas this distance is 4, so it's not working out, right? So you'll sometimes have to put a square root really on top, right? Okay? But see, this is so even when this is not such a good idea, statisticians started using this sometime in the 18th century and the 19th century for some good statistical reasons. But you'll learn that at some point the choice of using this rather than this was motivated by the fact that there were no computers. There were no fast desktop computers, because if you use this, then you can later on prove many results analytically without having a computer. Whereas if you use this idea at a distance, then many results you have to prove later on. You can't prove them analytically, but you have to simulate them from numbers. And for that you require fast computers. And clearly people like Gauss were very, very intelligent people, but they did not have fast computers. Right? So therefore they said, let's use this kind of a definition. Right? So the idea at the moment, we'll go by this old classical definition of distances, 3 minus 1 square and so on. Now, having said this, suppose you have numbers. Okay, suppose you have numbers, say x1, x2, x3, x4, x5, right? So the numbers x1, x2, x3, x4, x5. Very often, when I want to write x1 plus x2 plus x3 plus x4 plus x5, instead of writing this whole thing, I will write this as summation xi, I goes from 1 to 5. Everybody is used to this idea of writing things? Yeah? Okay, fine. So now, suppose I want to find a number x star, okay, x star, which has the property that the distance, total distance of x star from all these numbers is as small as possible. Right, so think of each of these numbers as, say, suppose you're buying a house, And x1 is a school, x2 is a supermarket, x3 is the railway station, x4 is a cinema, and say x5 is a hospital, right? Okay, you have to find a place which says that the total distance from all these locations must be as small as possible. You of course have the choice of being very close to the hospital and very far from this, right? In terms of total distances. You can be very close to here, but then you are very far from x4 and 5, so total distance might be high. So you want to find a location which which has a property that the sum of the distances of your house from all to all these locations is as small as possible, right? Let us call x star such a location. So what is the distance from x1 to x star? x1 minus x star square. Right, the idea that I've used, right? x1 minus x star square plus x2 minus x star square, x3 minus x star square, x star square. This is the total distance of x star from all the observations, all the locations, x1, x2, x3, x4, x5. Right? I'll write this more formally as, more compactly as summation xi minus x star square I goes from 1 to 5. Just a compact way of writing this. Okay, now I'm going to use a little bit of calculus. All of those who have forgotten your calculus, maybe don't worry about what I'm doing right now, but just remember the end point, right? Okay, whereas those who have still not forgotten their calculus, maybe it's not a very difficult step that I'm taking, but doesn't matter if you forgotten your calculus. Ajit will refresh it for you quickly, right? Anyway, it's not going to matter. What's going to matter is the last statement that I want to say. So what I want to do is, so this distance, what does this distance depend upon? This total thing depends upon x star, because x1, x2, x3, x4, x5 are all given, right?
Is x star the mean or it's just any number?
X star is just any number. I later on prove that it's the mean, right? Okay, because x star is any number which has the property that the distance, total distance of x star from all the numbers is as small as possible. Right? At the moment this is that number. Right? Okay. So I will write this as a function of x star, because if I change x star, this number will change. Right? Now I want to find an x star which will minimize this function, will make this function as small as possible. How would I do this? For those who remember the calculus, I differentiate this to x star and set that derivative equal to 0. For those who don't remember it at the moment, don't bother, stress yourself too much. At some point you'll get to know this, right? So what I'm doing is, yeah? Okay. By the chain rule, this comes out in the front and minus 1 will come out and so forth. So I'll have minus 2 summation xi minus x star is equal to 0. Can minus 2 be 0? No. So what is 0? This has to be 0. Right? So from which implies summation xi minus x star is equal to 0. Right? So what do I have here? If I write this, it is x1 minus x star plus x2 minus x star plus x3 minus x star plus x4 minus x star, which is equal to 0. Right? Sure? If I add these up, so if I rewrite this, this will be x1 plus x2 plus x3 plus x4 plus x5 minus 5 times x star. Right? 5 times x star is equal to 0. So what do I get? I get, if I solve this, I get x star is x1 plus x2 plus x3 plus x4 upon 5, or which is nothing but x bar. Right? So the x bar, the arithmetic mean, has an interesting property. It has the property that its total distance from all the observations equals 0. If I use the square idea of a distance, if I use the absolute as a distance, then x star would have turned out to be the median of the distance. X star would have turned out to be the median of the distribution, but currently we are thinking of squares, right? So therefore, X star is the arithmetic, so that's the arithmetic mean. Another property follows from this. So now instead of X star, I can replace X star by X bar. So X1 minus X bar is the distance of X1 from X bar, or the gap between. We'll call it the deviation of X1 from X bar. X2 minus X bar is the deviation of X2 from X bar. X3 minus X bar is the deviation of X3 minus from X bar. If I add all of them, I have the sum of the deviations from the mean, and here you see that the sum of the deviations from the mean is 0. Sum of the deviations from the mean is 0. So the reason why the sum of the deviations from the mean is 0. That's because the mean minimizes the total distance of all observations. That's right. Sure? Is this clear? No. Now following this idea of the distances, suppose I have got, suppose I've got 5 values, okay? I've got say x1, I've got x2, x4, x5. Okay? Now, if I write x1 minus x bar square, that's the distance of x1 from the mean, right? If I write x2 minus x bar square, that's the distance of x2 from the mean. If I write x3 minus x bar square, distance of x3 from the mean. If I write x4 minus x bar square plus x5, these are total distance of all the observations from the mean. I divide it by 5. What do I get? Yeah, but what do you